Hello, my name's Martyn Smith. I'm a professor at UC Berkeley, and I'm going to speak to you today about the hazards of occupational and environmental exposure to benzene. The toxic effects of benzene is something that I've been studying since around 1984-95, so almost 40 years. And I'm happy to relate some of what I've learned to you today. I'm very honored, first of all, to receive this award, from Dr. in memory of Dr. Stokinger, Mr. TLV as he was known. He led an inspirational life, and I've listed here some quotes from a profile of him by Dr. W.D. Wagner in Toxicology Sciences in 2021. It was quite clear that he had a long and distinguished career and made major contributions to toxicology. But some of the other things I noted about him was he loved to play tennis, playing well into his 80s. I'm hoping to do the same. I'm doing my best, playing a couple of times a week. And I also liked his quote about him, which says, "Well, I never was one to endlessly engage in a polemic of things. I think if they didn't like what I had to say, well, that's too bad." And that's really been, I think, a little bit of what I'm known for as well. So all due respect to Dr. Stokinger, and thank you again for this award. First of all, I should give a conflict of interest statement. I'm president and CEO of OneTox, which is a company that conducts research and forms business interests in the same areas as I do research on. And I am currently an emeritus distinguished professor of toxicology at UC Berkeley and the Kaiser Chair of Cancer Epidemiology. So where or how do you become occupationally exposed to benzene? Well, who is exposed, really? And it's mainly workers in the petroleum and petrochemical industry, including those working in refineries and bulk terminals, people like tanker truck drivers, anybody doing food transport, and even office staff have been shown to be exposed to higher levels of benzene in the general population who work in buildings on site at the industry location. Workers in coal-driven and coal gasification plants are also exposed, as are gas station attendants. Mechanics, auto body workers, painters, and others who use solvents and glues which may be contaminated with benzene are also potentially exposed. In some countries still, there are solvents and glues which are unregulated, which may contain up to 30 to 50% benzene in some cases. And this is typically in shoe and leather manufacturing, but also painters in such countries. We have studied some of those workers in the distant past. Also, seamen who are on board ships transporting crude oil and other fuels are also exposed. Levels in the captain's cabin has been measured to be as high as a part per million on an oil tanker. Now, benzene is used to make many, many things. Most plastics, it gets converted into styrene, which then makes polystyrene, gets converted into ethylbenzene and aniline. It's a starting point for the making of many, many different products, but none of these products are typically a source of significant exposure to benzene because the benzene is generally long gone, been converted into other compounds. But you may be environmentally exposed as a result of various other types of events, such as gasoline spills, which lead to a resulting groundwater contamination. This occurs in many communities, and I give a small example here that where gasoline or other BTEX containing solvents are leaking from a gas station, and the gas station and the gasoline is then it's less dense than water, and so it sits on the top of the groundwater. And as the groundwater rises and sinks with over time in the seasons, then The benzene can volatilize off the mobile phase of the gasoline and go into homes through entry into the crawl spaces and things like this. And it can also contaminate the groundwater and drinking water wells. And this is why you see many gas station sites which have had leaking tanks in the past standing empty in many cities as they require cleanup. Other exposures come from cigarette smoke and other similar sources of burning, air pollution, especially from mobile sources such as cars and trucks. Even if you're driving in commute traffic and you have air coming into your car, you are getting exposed to benzene. Garages attached to the home also leak benzene into the home through the gasoline and oil in the car. Gas stoves and other appliances have recently been shown to be sources of benzene in the home. This has led to some calls for the phasing out of gas stoves as they contribute also to global warming. When you pump gasoline at a gas station, if there's no vapor recovery system, you can be exposed to quite high levels for a brief period of time. In California, we're more and more concerned about forest fires and wildfires, as they're called. They also are significant sources of environmental exposure to benzene. More recently, the company Valisure has found that various spray-on sunscreens, dry hair shampoos, and other consumer products that contain propellants, including butane, that are contaminated with benzene may also be a source of benzene exposure to the general public. And even more recently, the same company has also reported that acne creams and other skin products which contain benzoyl peroxide may also break down, the benzoyl peroxide may break down to produce benzene in these skin products, which people apply on their skin, including many teenagers. So these are the major significant environmental exposures to benzene. Now, generally, though, the exposures to benzene of the general public has decreased considerably since the concentration of benzene in gasoline has been regulated. This is data that's shown from 2010, which shows you the concentrations of benzene in various fuels. And you can see throughout Europe, Australia, China, Canada, and California, and Brazil, the level was less than 1% maximum. But in the rest of the United States, it could be as high as 3.5 to 4.9%. This has now been regulated nationwide to be no greater than 0.62%. And so there has been a significant reduction in the Americans' exposure to benzene from gasoline. But elsewhere in the world, such as in Russia, South Africa, various other African countries, and throughout parts of Latin America and India, the levels continue to be quite high, and people are exposed to significantly more benzene than in the United States as a result. This just shows that the ambient benzene concentration in the United States declined since 2009. They continued to be at around 1 part per billion in most cities like San Francisco and other major cities. In other places where there are less regulation of the gasoline, there's also been levels as high as 10 parts per billion in places like Houston. But generally, the numbers have been decreasing significantly. However, even though there's been this reduction of the level of benzene in gasoline, a recent study that was featured in USA Today, published in Environmental International in 2021, showed that driving in commute traffic in certain areas, for example, in the San Francisco Bay Area and Silicon Valley, in the Los Angeles counties, and San Diego counties, you can see that the benzene level is above the no significant risk level for commuting daily in traffic. And also in some states, in some parts of California, exceeds the reproductive risk and developmental toxicity risk. So you can see that this is still a potential source of significant exposure, since many people commute to their jobs, and it's something that we have to bear in mind in terms of environmental exposures. So we now understand who's generally exposed, but let's have a brief history of the benzene toxicity. It was first described in some case reports by Sanderson, a Swedish physician, in 1897, and by Lenoir and Claude, they identified a similar case where there was evidence of significant toxicity to the blood-forming organs in the form of aplastic anemia or severe dysplasia, which was life-threatening. This was followed by numerous other case reports of when benzene was introduced as a solvent. And this was actually in a bicycle repair factory or a manufacturing facility in Sweden, as bicycles had just been invented and people wiped down the rubber tires with benzene. And by 1909, the general symptomology of damage to the blood and to the bone marrow had been described, and hygienic instructions, industrial hygiene instructions, started to appear. And it was described, for example, by Alice Hamilton in the 1920s as being an insidious toxin in the workplace, and people started to recognize its dangers, not only to the blood-forming and bone marrow systems, but also to your immune system, since it was shown that tuberculosis and pneumonia, you were more susceptible to them if you had been exposed to benzene. Now, the first description of an association or case report with benzene and leukemia was in 1928 by Deloria and Lugano. So it was from Italian workers. And there were then multiple case reports, and the American Petroleum Institute commissioned a report in 1948, which described several of these cases of leukemias occurring in people exposed to benzene. And Eugene Cronkite, the well-known hematologist, described benzene as one of two industrial leukemogens along with radiation in 1961. But really, it wasn't really until these additional leukemia cases, which were reported in shoemakers in Italy by Vigliani and Forni, in Turkey by Aksoy during the 1960s and 70s, that people really realized that benzene almost certainly caused leukemia in exposed people. They were studying people who were extremely highly exposed as shoe workers and leather makers in these facilities, and they were exposed to 100 parts per million benzene and things like this, and they described multiple different types of leukemias and what we would now call myelodysplastic syndromes in these workers. But in 1977, in a very well-designed epidemiological study done by NIOSH, Peter Infante and others described an excess of leukemia deaths in the so-called pliofilm cohort, where the factories in Ohio were making pliofilm rubber. And this was published in The Lancet in 1977. And this really sort of led to the conclusion that benzene definitely causes leukemia. There were also subsequently reports in China that there was an excess of leukemias in Chinese factories using benzene in 1987, which formed the basis of many studies by the National Cancer Institute in collaboration with Doctors Yin and Li at the Chinese Academy of Preventive Medicine in Beijing. And finally, in 2003, Dr. Debbie Glass and others in an Australian cohort called the Health Watch cohort described in a nested case control study within that cohort an excess of leukemias with relatively low levels of benzene exposure, not exposures of the type that Vigliani and Aksoy described, but much lower levels in the less than in the 2 to 4 part per million years types of range, rather than the very high doses that were seen, and seeing an excess of leukemia in those individuals. Now, this just is a picture of Dr. Aksoy from back from a review of his life's work and his great book called Benzene Carcinogenicity, which has it's just full of great information. And I had the pleasure of sharing a taxi with him one time, and his work was clearly pioneering in the whole area of benzene toxicology. This is the NIOSH study by Infante and others, which described an increased risk of leukemia, especially myeloid and monocytic leukemias in this population compared to controls. And this, in the study in China, there are 12 different locations in China that were studied. This very large study, which involved 75,000 workers or so that were investigated in a large cohort. Results from the China study, early ones, suggested that not only was AML produced, or acute myeloid leukemia was produced by benzene, but also myelodysplastic syndromes, or MDS, and non-Hodgkin lymphoma in this Chinese group, and the well-known effect of high doses of benzene, aplastic anemia, that was first reported really by Sanderson back in 1897, was also seen in these Chinese studies. This is the paper by Glass, and as you can see, with cumulative lifetime benzene exposures of greater than 8 parts per million years, you see a significant increased risk of acute non-lymphocytic leukemia, or AML as it's called, also called. And as you increase the cumulative lifetime exposure, you see even increased risk of leukemia overall, but only 2 to 4 parts per million years, with a 6-fold increased risk. So this findings of much lower levels of benzene raise concern further about how dangerous benzene was in the workplace. This is the dose response curve for leukemia with cumulative lifetime exposures, and you can see there's kind of a trend towards nonlinearity, where you get an increase at low concentrations, which then starts to plateau out. Of course, given the error bars, you could also draw just a linear line through this, but the dose response curve for benzene apparently is either linear or supralinear, with there still being effects of extremely low levels of benzene exposure. So these studies led to alterations in the OSHA standards for benzene in the PEL, the amount allowed to be in the air in an 8-hour workday, retain weighted average. The Infante study led to the change from 10 ppm to 1 ppm, but it was almost 10 years after the publication of Infante's study that the number was actually lowered from 10 to 1. In the TLV in 1997 was revised to 0.5. The OSHA standard is still 1 ppm as of today. Back in the 1990s, also, NIOSH recommended a 0.1 ppm occupational standard, but it was decided by the ACGH at that particular time in 97 that 0.5 was sufficient. And the air pollution standard for non-cancer effects, just to put it in perspective for EPA, is about 0.03 ppm, or 30 parts per billion. Now, the recent history of the TLV is shown here for benzene, and as you can see from 1997, which I just described, the level of 0.5 ppm, which was proposed, was adopted, and there was also confirmation that it was a human carcinogen, and there was a TLV STEL that was set at 2.5. This was suggested to be changed as a result of the work that I'm going to describe in the next few slides, that has now been adopted in 2023 that the level should be, for the time-weighted average, should be 0.02 ppm. This is a huge change from the original TLVs, and it's also 50 times lower than the OSHA PEL. So clearly something is amiss with the OSHA PEL, and we should be thinking about asking OSHA to change that. There also was a removal of the STEL because it was considered that doses of benzene at relatively low levels posed a significant risk, and that there was no need for a STEL TLV. So I'm very pleased to see this change and give you some background to it. This just shows the actual description, for example, from Chemscape, that there was this lowering to 0.02 parts per million, and the descriptions of why this change was made are in the TLV documentation. But the main basis, I believe, of this change was the findings by Schnatter and others, which were published in 2012, which was a pooled analysis of both acute myeloid leukemia, or AML, and myelodysplastic syndromes, or MDS, which used to be called smoldering leukemia or pre-leukemia. I'll describe them a little bit more in general, but they are a form of cancer, and they can be lethal. I mean, for example, Carl Sagan died of MDS. And what happened in this particular study is these workers, Dr. Schnatter is an epidemiologist from ExxonMobil. They pooled the international studies of petroleum workers from Australia, Canada, and the United Kingdom into one large study. And when they did this, they found that a cumulative exposure of only just around 3 parts per million years and above would produce a significant 4-fold increased risk of MDS. It's important to note that AML was elevated in terms of risk, but was not significantly increased in this same group. But this tends to show that the MDS effect is actually appears to be the most sensitive cancer endpoint for benzene, and led to a lot of consternation in terms of this at this level, because it shows that at 3 parts per million years, even 0.1 ppm for a 40-year work history is not safe, because you would end up with a 4 parts per million year exposure, and this would, according to this study, lead to a 4-fold increase of your risk for getting MDS. So benzene causes AML, but it also causes other myeloid neoplasms that may transform to AML. The most significant of these is myelodysplastic syndromes, or otherwise called MDS, which are actually now called, under the new WHO guidelines, myelodysplastic neoplasms. This is because I think when they were called syndromes, some people didn't realize they were actual cancers. There are also a set of cancers in the bone marrow called myeloproliferative neoplasms. These are things like polycythemia vera, chronic neutrophilic leukemia, chronic eosinophilic leukemia, and thrombocytopenia. And these are also have been associated with benzene exposure, as has chronic myeloid leukemia, which is another form of myeloproliferative neoplasm, but it has not been so strongly correlated with benzene exposure as AML. So the differences between MDS and AML are really, the main difference is about the percentage of abnormal bone cells in the bone marrow. Under the original classification, which was called the FAB classification, the conversion of MDS to AML was thought to occur with a 30% level of abnormal bone marrow cells. But the new guidelines now show that the World Health Organization, that MDS transforms to AML when 20% of the cells in the bone marrow are abnormal. So this is really the main difference between them. They contain many of the same features of their cells and the same sorts of types, but they are somewhat different diseases and they're treated differently. Now, the former WHO categories of MDS, there were then subgroups of those, and I'll tell you a little bit about those because of some slides that are coming up a little bit later. MDS was previously split into these 4 different subtypes called MDS with refractory anemia, MDS with refractory anemia ring side aeroblasts, and MDS RCMD, which is very common in China, as I'll talk about, and MDS REB, refractory anemia with excess blasts. Basically, when this exceeded 5%, it became called RABE2, and less than 5%, it was RABE1. So you can see here that typically with these other forms of MDS, the level of abnormal cells in the bone marrow is typically less than 5%, and they transform slowly into AML. REB commonly transforms into AML and has many more blasts present in the bone marrow. Now, one of the earliest studies which found an association with myelodysplastic syndromes and benzene and solvent and gasoline exposure was that of Sarah Strom and others from MD Anderson, where they found an association of MDS with smoking, with pesticide and agricultural chemical exposure, and benzene and solvent and gasoline exposure. Wine drinking, if it's any comfort to you, appeared to lower the risk, although this has not been repeated in other studies. Around the same time as Strom published this, we published a paper in Science on the hematotoxicity of workers exposed to relatively low levels of benzene in China. We deliberately identified a factory where exposures were typically below 1 part per million. In fact, there were a large number of workers, more than 100 in this factory, who never had exposures above 1 part per million. And we monitored these workers very carefully. We collaborated with our local Chinese investigators there, but also with the factory managers and factory staff who were incredibly helpful in performing the study, and wanted us to show that if there were adverse effects of these relatively low-level exposures to benzene, that what controls could they then put in place, and what would be the sources of this benzene. And we found that the major source was actually this innocuous-looking glue, which actually had a solvent in it that was 30% benzene. And so very high levels of exposure were produced by people who were using this glue, largely to glue the soles of shoes onto the bottom of the shoe. Okay. Now this paper basically showed that at exposures less than 1 part per million, less than the OSHA PEL, you got significant increases in, or significant decreases, sorry, in the level of white blood cells of all different types. And you actually had an effect, which we showed, which I don't really have time to show, but there was an effect also on the early progenitor cells and stem cells in the blood and bone marrow. They were also depleted by exposure to benzene, which is kind of what we would know, but it demonstrated it in humans that that was a mechanism that was working, and it was working even with workers who are exposed on a continuous basis to less than 1 part per million. Showed also that the level was unsafe. The typical level of exposure for all of these workers was around 0.5 ppm, but we showed by looking at the data with spline analysis that there was an evidence of a supralinear type of response, where at higher levels of exposure, the effect on the bone marrow appeared to plateau out a little bit, but there were still significant effects at low levels, which caused a rapid drop in the levels of white blood cells in the blood. There didn't appear to be any sort of threshold for this type of effect within this population. So this was probably because there was a a certain number of susceptible individuals. We also studied the genetics of susceptibility, which I don't really have time to go into, but there were multiple polymorphisms in different genes which conferred susceptibility to benzene, most notably in an enzyme called NQ01 or NADPH oxidoreductase, quinone oxidoreductase 1. Vlander and subsequently have looked at this exposure response curve in terms of cumulative part per million years and the risk of benzene-induced leukemia, and have again found that in all these cohorts, when they're combined, that there is a supralinear type of effect, that you see effects at cumulative exposures which are below 100 parts per million years, quite different to ones at higher. So higher concentrations, it tends to plateau. And this fits with what we understand about benzene metabolism. Early work by Steve Rappaport's group using samples from this Chinese cohort showed that the formation of adducts of benzene oxide on albumin occurred at a higher rate per molecule of benzene, if you like, or per part per million of benzene at lower concentrations than it did at higher concentrations. And he went on to do quite considerable modeling of this, and it's looked at a 10-fold reduction in slope at high concentrations. And there seems to be a saturation and also very large inter-individual variability in benzene metabolism and metabolite formation. And in a paper from Environmental Health Perspectives, he predicted concentrations of benzene formed by two different pathways that would explain this supralinear type of metabolism. And it appeared that there was one particular pathway which occurred at very low levels of benzene exposure, which produced the majority of the metabolites when you were exposed to, say, environmental levels of benzene, lower, very low levels. Whereas a second pathway kicked in, mostly notable to be probably CYP2E1 in the liver, at higher concentrations of benzene. And so this idea of there being two pathways of benzene metabolism is something that's still being controversial and is still being debated. There are still no clear ideas of what that low-level pathway really is. It's thought it could be in the lung, and it certainly is a possibility. Also of interest, I think, is the fact that recent work has shown that the level of benzene exposure in the US population, which was always thought to account for only a small percentage of the AMLs and MDS, is in the general population. But it's found in the study of all of the cases that they could find in a registry of AML and an MDS in this population in Minnesota, that 8 to 16% of the AMLs were related to benzene exposure in some way, and that there was a twofold increased risk of AML and benzene exposure. In the Texas study done by Sarah Strom, the study of AML in 2012, she described how the level in men, like 40% of the AMLs in Texas, could be related to exposures in the workplace from benzene. And so hopefully with the new TLV, this will decline, but you can still, there are still significant cases of benzene exposure causing AML in the US population. And there, interestingly, the cases associated with benzene had more likely to have genetic abnormalities in these cases. We also looked at non-Hodgkin lymphoma. I don't have time to really discuss this in great detail. There are two papers by myself and Craig Stonemouse and me and others, where we looked at various refinery cohorts, noted there was a strong healthy worker effect, adjusted for that. And the latency period is also likely to be very long for NHL compared to AML in general. But it does support an association between benzene and NHL. We've also found in meta-analyses, when we put all of the studies into a meta-analysis, that childhood leukemia is associated with exposures to benzene, especially in location close to proximity to gasoline stations. And it was especially notable for AML, childhood AML compared to childhood ALL. We saw a 2.2-fold increase risk for AML with exposure to benzene, either in utero or to the parent or to the child itself. And to finish with then, the last few minutes is, how does benzene actually cause leukemia? We've been investigating this for many years and have some ideas, and again, there is some controversy about it. We know that benzene has to be metabolized in order to produce leukemia. There is a complicated metabolism forming, first of all, benzene oxide, which may break down to muconaldehyde and muconic acid, which could be also, the muconaldehyde could also be a toxic metabolite. It's converted non-enzymatically to phenol, which can become hydroquinone, which can then become benzoquinone in the bone marrow through activation by myeloperoxidase. It can also become benzene triol or trihydroxybenzene. And catechol is formed from benzene dihydrodiol, which is formed from benzene oxide being converted by epoxide hydrolase. This can also form a diol epoxide, which Franz Eusch and others first proposed was a toxic metabolite of benzene, and that could play a very significant role and needs to be further explored. But we've also explored the ideas of the quinones at the bottom being the toxic metabolites of benzene. And together with Richard Irons and David Eastman, we showed early on that the combination of phenol and hydroquinone would basically produce the same effects as benzene on the bone marrow in mice. So how is benzene then producing the leukemia once it produces these toxic metabolites? Well, its metabolites can form DNA adducts that lead to single and double DNA strand breaks. It can cause oxidative stress through a generation of oxygen radicals, and these lead to the formation of 8-hydroxydeoxyguanosine and 8-oxo-DG, which are potentially mutagenic lesions in the DNA. David Eastman and others have also shown that its metabolites will inhibit topoisomerase II, leading to chromosome rearrangements. And we have shown, and many others have shown, that exposure to humans to benzene or human cells and its metabolite, or exposure of human cells to its metabolites, produces numerical and structural chromosome aberrations and micronuclei that are associated with increased cancer risk. And to summarize some of our studies, in benzene-exposed workers, we have shown that there are very specific chromosome aberrations related to leukemia, AML, and MDS, myeloid neoplasms, such as the loss of chromosomes 5 and 7 or deletion of parts of them, the translocation of chromosome 8 to 21, and trisomy of chromosome 8, plus the chromosome changes associated with non-Hodgkin lymphoma, deletion of 6q and translocation 14, 18, as well as non-random aneuploidy can all be observed in benzene-exposed workers. And in lymphocytes, we treated with the metabolite, benzene metabolite hydroquinone, abbreviated here as HQ. We also saw these effects. But also significantly in CD34 positive early progenitor stem cells from the blood, hydroquinone produced this losses of chromosome 7 and trisomy chromosome 8. And Richard Irons and others found very similar results where they found changes in chromosome 7 and chromosomes 5. So very similar. So it's quite clear that the hydroquinone and benzene metabolites can produce these changes that were commonly observed in leukemia. So this led me and others to suggest that the benzene-induced myeloid leukemia was quite similar to therapy-related AMLs produced by things like alkylating agents, where you would typically see the loss of chromosome 7 or deletion of 7q on loss of chromosome 5. So alkylating agents which produce leukemia. That's the type you see. Whereas topo-2 isomerase inhibitors, which which benzene can also, metabolites can also be, you again see this loss of deletion of chromosome 7q or translocations. And you see things like translocation 1517 or rearrangements at 21q22. That's, for example, TA21 and inversion 16. So these were the types of things that we saw with benzene. And it was quite different to de novo cases, which commonly had a more normal carrier type. So this is what in the Annual Review of Public Health in 2010, I published this concept. But a subsequent study in China suggested that benzene AMLs more closely resemble de novo than therapy-related AML. Richard Irons and others looked for these particular chromosome changes that I just mentioned, which were produced by benzene in a petri dish in exposed workers, etc. But found that actually that the level in benzene-induced AML or AMLs in China, they classified as benzene-induced AMLs, were less likely to be like therapy-related leukemias. These are the therapy-related leukemia ones from a cohort in Chicago that they compared them to, where you saw typically these -5, -7 effects. Didn't see that in the benzene-exposed AMLs in this study in Shanghai in China, nor did they see changes in 821 or 1517. Now, there are also findings from this same group about different subtypes of MDS in this same cohort in China. And this group in China is quite unusual. These benzene-induced AMLs were all around 30 years of age, so very young. And they're comparing those then to people who are a lot older getting benzene-induced leukemias or getting de novo leukemias in their late 60s, 70s, and 80s. So they're very different, and there was a relatively small number. And this really doesn't fit with our current understanding of how benzene works. And it also doesn't really fit with other studies in China in a similar cohort by Wang and others, who found that the most common chromosome changes in these benzene-exposed, benzene-induced AMLs in their study was 821 and T1517, which would suggest that this topoisomerase 2 mechanism was the main one. And this again was in very young patients. And so it's quite different to what Irons and others suggested in 2013, that it's this de novo cases with RAS mutations and normal carrier type that's the mechanism of benzene, and that the major mechanism by which benzene, as they propose it, is the cloning out or the cloning out of the leukemic stem cells. Now, the issue with all this is that there is also, by the way, quite a lot of differences between these groups of diagnosis in China and in the USA. I just won't talk about this very much, but most of the MDS in China is RCMD in carrier type, like in subtypes, 70% or so. This is quite rare in the United States from our study from 2008, using SEER data and national data. It's only around 2%, and the majority in the United States at that time were in the unclassified or not otherwise known, around 60%. And so very different setups in China in terms of the types of MDS that are produced. And so whether you can truly extrapolate these findings from China in terms of the AML subtypes and MDS subtypes is an open question, I think. The mechanism, though, is likely to involve a multitude of effects. It's unlikely that benzene produces MDS and AML only from its genotoxic effects. It has a multitude of effects on the blood and bone marrow, and it's more likely that a combination of these, including the cloning out of the leukemic clone, is important. And I think this is demonstrated by the fact that there is strong evidence that the benzene has at least 7 of the 10 key characteristics of carcinogens, according to IARC from its monograph. Here are the 7 out of the 10 listed. This suggests to me that benzene is working through multiple mechanisms in producing both AML, MDS, and other forms of bone marrow damage and bone marrow cancers. And also non-Hodgkin lymphoma, in my view, through these multitude of effects. And we first described this idea of there being a multitude of effects that produce benzene-induced leukemia in this paper by Cleona McHale, Luping Zhang, and myself in 2012. And finally, as I'm out of time, I want to thank all of my collaborators over the years on all of this, especially Gulan Li and Sonyan Yin in China, Nat Rothman, Qing Lan, especially at the NCI, Will Vermeulen and Steve Rappaport did all of the work related to industrial hygiene in this work. My colleagues at Berkeley, including Luping Zhang and Craig Steinmaus especially, along with Cleona McHale, have contributed immensely to this work, and I thank our funders from the NCI, from NIHS, especially the UC Berkeley Superfund Research Program, for helping with this. And thank you very much for your attention.